All right, our next theorem is something called the Folkmans theorem. Let me state the theorem. So this is, so for every R coloring of set of positive integers and a positive integer k, there exists a set S of k positive integers such that all of some of the let's say a in T for all T which is subset of S is non-empty have the same color. Right, is it is it clear? No matter how I color the set of positive integers with finitely many colors, there exists a subset of size k such that any subset has, for any subset, if you look at the sum of its n member elements, then this sum have the same color. So let me define some set. So, but anyway, yeah, so this is a theorem that we're gonna prove. Of course, you can prove it from Radol's theorem, because, like for instance, if k is 3, then you're actually solving something like this. Right, something like solving something like this, where we also need x1, x2, x3 are distinct, but there's a way to guarantee that, which I will not mention. So if you can prove that this system is regular, then that will be a step towards proving Folkman's lemma, theorem, because all the sums will be distinct. All the sums will have the same color. But still, oh, is this passed away? If you want to say that these are distinct, one way to do it is x2 is equal to x2 minus x1 is equal to g1, x3 minus x2 is equal to g2, right? So this way, if I add these things, anyway, okay. Anyway, this side remark. But we're gonna show the direct proof based on the van der Waals theorem. All right. So even though we stated Folkman's theorem in an infinite version, I'm gonna show you the equivalent finite version. So we're gonna prove the following form. And this is equivalent because of the compactness. For every integer r and k, okay, so for let me write, for all integers r and k, there exists n, which is n based depending on r and k, such that for every r coloring of n, there exists a1, a2, ak with all of them and most n when I sum them, that's at most n, such that the color of sum of ai for I, which is subset of n, this is not empty, depends only on maximum of I. Okay, so this is the one. Oh, no, this is not what I want. This is the lemma that I'm going to talk about. I was confused such that all of them that all of sum ai I in I for non-empty subset have the same color. That's the finite version. Let me point out that there was a typo. So the set I is a subset of k, right? Of course, because you want this index to be the subset of 1 up to k. And in the video, I may have same kinds of mistakes. At the end of the video, I will explain all the places where to fix it. But we're going to prove a weaker version as a lemma first. So it's the same setup. Almost the same setup. Copy and maybe paste here. And let me copy this. And paste here. Right. So our goal was to prove that every subset has the same. Every subset has the sum having the same color. But now the new goal is the sum depends only on the maximum. The color of the sum depends only on the maximum elements. And that's easier goal, of course. But once you have this, then it will help us to prove the full theorem. So we're gonna proceed by induction on K. And it's trivial if K is 1 because there's only one subset, one non-empty subset. So assume K is bigger than 1. And we're gonna take n to be twice van der Waals number of r colors, n of r minus 1 and k. Oh no, it's induction on r, so I'm gonna reduce k. We will take this way. Now let chi be an r coloring of numbers from 1 up to n by considering n over 2 plus 1, n over 2 plus 2, up to n over 2 plus n, we find an arithmetic progression. monochromatic. Arithmetic progression of length d in this set. Here's another typo. This n should be n over 2. Right? So you have, since we have a coloring, R coloring of 1 up to n, and we only look at the second half. So what I mean is, we can find there is AK and D such that AK plus D, AK plus 2D, AK plus D minus, oh, it's length D. Oh no, length is not D. Length is this number. But since we are applying van der Waals, length nRK minus 1 and RK minus 1D. So we have all of them have the same color, and AK is bigger than n over 2, and AK plus NR minus is less than or equal to n. Okay? Now this means that n of RK minus 1 is less than, this number is less than n over 2. Now we identify, okay, now let me continue. Right. Now we identify the multiple of the D with the G, right? Then apply induction hypothesis. Then what do we get? We get we find A1, A2, AK minus 1. Each of them are the multiple of D, and AK minus 1 is less than or equal to this van der Waals number. No, not van der Waals number, the induction requirement, and all such that the sum of AI for I and I for all I subset of 1 up to n minus 1 for all non-empty subset have the same color. Now the thing is, what's going to happen with this plus AK? Well, the thing is, the sum oh, I see. Yeah, actually, not only the last one is less than that, but we want all the numbers have the color. So this thing, their sum is less than or equal to n to n over RK minus 1. So their sum plus, so this is, yeah, but anyway, so this is something less than AK plus NR. I mean, it's definitely less than this, right? I'm trying to decide whether I need +1 or not. So it's possible that this is equal to that, right? So that means I may need one more length. So let's add +1 here. So I'm fixing here. Then I'm removing -1 here. So that means I'm gonna have length +1. All right, so that's gonna be a all right. Yeah, so this will be safer, right? Oh no, what's going on? Let me fix here. We are coloring numbers from 1 up to this van der Waals number. So it's a W. Yeah, it's WR and RK minus 1 plus 1. What's going on? So then all the partial sums have the same color. Oh no. Let me go back. So this is at most n of RK minus 1. And then when you end up is, yeah, this is correct because I'm coloring these numbers from n1 up to nRk minus 1. We have this k minus 1 integers whose all the sums have the same color. No, whose all the sums. What's going on? Yeah. let me fix it. The color of this depends only on maximum I. All right. Yeah. So that's right. So we're trying to prove that there exist k integers, so that all the sums, the color of the sum depends only on the maximum elements in the subset, and we are applying induction hypothesis. So there exist k of them. There exists the k minus 1 of them. All of them are the multiple of D, so that the color of them is Right. This sum is the most, you have to multiply d. Right. That's right. Now now everything works out. So this is the most k minus 1 d. All right. So that's it. So we still have so the sum of a1, a2, ak is at most ak plus nrk minus 1d. And now note that this is a multiple, right? Sum of ai is a multiple of t, and it's between 0 and n of rk minus 1d. Thus, if k is in I, then for all subsets I of n, the sum of ai have the same color. This is because we know that all of this, okay, let me look at the left of the screen. We know that all of them have the same color. If you don't have AK, then by induction, all of these, if you don't have AK, then by induction, all of this thing have the same color depending on the maximum, right? So this proves the theorem. Yeah, there were so many distractions. People call me and I was not used to focus. Anyway, so this is a key lemma. So this lemma says that I can pick k integers so that for every subset, the sum of the elements depends on the maximum of them. All right, so now let's prove the Folkmans theorem. Right, how do we prove it? Now it's easy thing, right? So find a1, a2, I'm gonna say r minus 1 k plus 1, so that the maximum, no, the sum of ai depends only on maximum of I. Okay, for each I, for each non-empty subset of, for each non-empty subset of this thing. This can be proven from, this is deduced from the previous lemma. Now, then by Pisonal principle, R of them, no, actually K of them, induces the same color. What I mean is that if for each AI, there is a one color associated with I, such that any subset which having AI as maximum element will have the same same color in the sum. And then since we have this many indices, by Pisonal principle, K of them will induce same color, and pick those K. And that's it, right? So that will prove the Folkmans theorem. Again, there were a few typos. Some of you may have already noticed. So first typo is the number of this number. Is instead of n, I is a subset of 1 up to k, right? Because you have a a1 up to ak. And there are a number of places where I made the same kind of errors. Whereas, yeah, so here is instead of m minus 1, it's k minus 1. And here's k. All right, so that's one kind of errors. And another mistake was to color, over here. This has to be n over 2. So n over 2 plus n over 2 is n. So that's why we color integers from, since we have coloring from integers from 1 up to n, the previous writing didn't make sense, right? So that's it. So we have two fixes. So one is about the indices. So I is a subset of this thing. And the other is this thing is up to n.